Thank you very much, first of all. And yes, of course, I promise you, I brought some PhD math with me, but not to do the actual math, but to show you, like from a developer's perspective, what you actually have to handle with when it comes to doing quantum computing. Yeah. So in the previous talks, in the first talk, I think we've seen the basics from physicists, etc. How quantum computers look like, and we've seen qubits in their essential manufacturing. Then we've seen something about questions about algorithms and what does quantum advantage means, etc. And now I think my talk puts another perspective on the whole quantum stuff, namely what as developers, which we are typically, what do we have to expect when it comes to programming quantum computers? When it comes to implementing those magic quantum algorithms, doing stuff that we can't do it today, etc. And of course, I want to lift this discussion also to an argument that we see, that we learn from a German project, a lighthouse project, how we should, say, develop quantum proof of concept as of today in order to develop them further in the future when the quantum computers get ready. Yeah? So this is all about the stuff of the Apification. Yeah. So yeah, I think I can skip the slides. Michael, my name, as already introduced. So I've three main topics brought with me. The first one is, from a developer's perspective, what makes quantum computing so special, also different to what we actually do now everyday jobs. Yeah. And a second point derived from that, well, it shouts for kind of abstractions that we need in order to deal with quantum solutions in real-world applications in the future. And the last point, nucleus of a quantum software community in Germany. I want to talk about some specifics about the endeavors in Germany, because lots of stuff going on there right now. Lots of money is spent from the government to boost not only the development of quantum computers, technical stuff, the physicists, etc., but also to boost the software side, to actually develop quantum algorithms, but also to bring them to real-life scenarios, etc., to use cases, and to test how far we can go with current use cases with that. So, but first of all, starting with quantum ingredients in a nutshell. So, for all of you who have visited the previous talks about the quantum stuff, you have heard about the superposition entanglement stuff, but I want to bring now the PhD math into play. Yeah, for my friend here. Finally, yeah. So, but first of all, again, maybe another picture to draw a picture. What can we expect when you talk about superposition? So, in the classical world, of course, you see on the right side from your perspective. No, from the left side, from your perspective. Yeah, you see this the classical bits. So when you can just imagine it like a lever being in either the one state or in the other state. So at one time, our classical bit or lever is in the 1 or 0 state, and the qubit, on the other hand, this mysterious superposition thing can exist at the same time, so to say, in both states. Of course, this is just an analogy, and of course this always comes with some problems in interpretation. But what comes into play when we talk about quantum bits, qubits, is always the probabilities. Yeah, we can't say anymore that once a qubit is in a quantum state, in a superposition, that it is either 0 or 1. We just can say, well, with a certain probability, it is in the state 0 or in the state 1. Yeah, so probabilities come into play. And the math will follow on the next slide to show you that. Yeah. So this is the fundamental difference between classical bits and quantum bits when it comes to superposition. Yeah. One ingredient, superposition. Yeah. And then, of course, if we do calculations with those qubits in superposition, it means what means a calculation? It just means that we change those probabilities of the qubit being in the one or in the other state. Yeah, this is actual calculation on a quantum computer. This is what a quantum computer does. And of course, it does not just on single qubits, but on whole registers of qubits, but I will come to registers later. Yeah. So quantum computing just means we measure probabilities of a qubit being in the one or in the other state. Okay, so therefore we also have to consider running a quantum algorithm doesn't mean just running it once and having a result. It means we do a probability experiment and we have to run it several times. So generally, it's called executing shots on a quantum device. Yeah, and to get some nice probabilities for getting results out of algorithm, we typically have to execute one algorithm or thousands of times on the actual quantum device to get a result. Yeah. So how can you represent? We had this lever, yeah, but how can you represent a qubit actually? So you have seen the block sphere, I think, in the talks before, but to just, let's say, hide these mythics about superposition, etc., let's just assume that a qubit is nothing else than, say, a vector within the sphere, starting in the middle of the sphere and pointing to some point on the surface here. Yeah, and if we now talk about superposition, for instance, yeah, a superposition, perfect superpositions, meaning, for instance, of a qubit being either in a state 1 or 2 with a probability of 50%, then just intuitively, if the state of the qubit is just this vector here, yeah, this vector, just imagine if we put the vector here, just in this plane, and put it here, and the poles 0 and 1 represent the classical state. Yeah? If we put this vector exactly here, then we have an idea what it means that a qubit is 50-50% in the state 0 and 1. Because if we measure it, sometimes it will collapse. Let's say it would be projected on this side, yeah, and being then 0, and sometimes on the other side. So this is the whole mystics about superposition, yeah. And of course, this is then, you have not just this superposition, you can also have other probabilities, but this is essentially what it means to have a qubit in superposition. Yeah? Just being not just here at the pointing to the poles, but having it somewhere. And the calculation, again, just means, hey, we just shift this vector around this the surface, pointing to other points on the sphere. These are calculations. Okay? So, now the math, as promised. I don't want to do the math with you in terms of calculating it. So I just want to give you an impression from a developer's perspective. My background is in computer science, so when I first got into quantum stuff, I was kind of shocked. Yeah, having to deal with Greek letters again, and like, whoa, what's that? I can't read it. That's like Chinese letters in the first place. So, but again, what's a qubit? Yeah. We have seen this kind of a vector in the block sphere, yeah, and we have probabilities, yeah, and we have seen the poles 0 and 1. So we can also just easily write a qubit as a quantum state, like this one here, yeah, and stating here we have here an amplitude for being in the 0 state and another amplitude for being in the 1 state, yeah. So, and without further math, yeah, it's just we can interpret this alpha and this beta with calculating the value here and squaring it as the probability of being the qubit in the state 0 or in the state 1. Again, just think about this vector, yeah, on this block sphere. Meaning, we can just easily write qubits and the states of qubits this way. We can put here, let's say, the probabilities as alpha and beta, and then we have described the quantum state within a qubit. And of course, yeah, man, we live in the real world. If we measure those probabilities, of course, both have to sum up, the alpha and betas have to sum up to 1. Because otherwise, yeah, where should the level be? It has to be in 1 or 0 if we measure it. Okay, and another to put another thing away of mystery is, well, these special notations here are just vectors. Yeah, back to vectors. On the left side, you see, for instance, another notion of this alpha and beta, not with this notation 0 and 1, but just with writing this vector and this vector. And then we'll see, well, okay, then quantum computing seems to be just calculating with vectors and matrices. Yes, that's it, essentially. Okay. So of course, then now we just don't have to deal with single qubits. We want to make richer calculations, etc. And therefore, we put some of those qubits together, and then we can form so-called quantum registers. Quantum registers, nothing different than just having multiple of those qubits together. Yeah. And now there's something special, because we're working here in a vector space, and one register means then we have some curious behavior when it comes to these vectors, yeah. Because a register is a tensor product of each of the qubits. What does this mean? I try to show it to you here. So if we add another qubit, the space of possible, let's say, probabilities which we can represent is extended by 2 to the power of n here. Yeah, so the space, the actual computational space which we have, increases, and this is also one of the things why it's not that easy to simulate quantum computers. First, in the talk before, we learned we can simulate them, but simulating 30 qubits and more, it's getting really hard. And I think I've never seen simulations above 50 qubits or so. So you see, our classical hardware, of course, can simulate quantum computers, but there is a limit. And this stems especially from this tensor product when it comes to quantum registers, because you can see here I calculated for you the tensor product of 2 qubits and 3, and then here see 4. Well, there was the graphic. I had not enough place there. And if you think now 2 to the power of, let's say, 50, well, this is a huge vector. And operations on these vector operations in a quantum computer are nothing else than calculating or multiplying matrices, special matrices, with these vectors. You see, quantum computing deals with huge matrices, actually. And this makes them actually also hard to simulate because of the huge matrices. Yeah? So then, classical to quantum register. Also, I try to give you an intuition about what does this superposition mean and operating on all the states. Yeah. So a classical register, of course, yeah, you can represent 2 to the n minus 1 values, different values, but just one value at a time. Yeah, how our computers work. And now, because we introduced those probabilities for the different states being actually in of a quantum register, we can represent these 2 to the n minus 1 states at once with probability. Don't forget those probabilities. Yeah? Meaning calculating on the whole register means we apply let's say we shift this vector, yeah, now of course in a n vector space, just around. But one calculation, one operation on this register means we can manipulate the probabilities of each of the qubits at once. And this is kind of cool. Yeah? This is also called the quantum parallelism. And then the second thing, we have this thing, entanglement. So entanglement is therefore very important because on the one hand, you needed to build an actual universal quantum computer doing all the stuff a classical computer can do. And there's a proof that if you want to reach with an algorithm an exponential speedup, you have to use somehow entanglement. So without entanglement, no exponential speedup. Yeah? Superposition maybe can bring you a quadratic speedup, etc., but entanglement is important. So now, what is entanglement when we come back to our mathematical notion? Yeah? I've drawn here a quantum state, and we have here a register of 2 qubits. Yeah? And the qubits are either in the state 0, both, or in the state 1, with a probability of 50%, half. Yeah? Because if you calculate it, you have half this, half this. Yeah? So now entanglement brings you one advantage. In the previous talk, Sebastian mentioned quantum algorithms try to save steps in calculating solution. And here, yeah, kind of intuitively, you can see it already, yeah? So because our register is either in this state or in this state. And now something interesting happens if we measure this first qubit. The first one is 0. We just look at the first qubit in the register, being in this entangled state. Yeah? We immediately see that the second qubit can just be also 0. So just looking at one qubit, we immediately get information about the second qubit. We don't have to look at it. We immediately understand and know the second qubit must be 0. And this is the second ingredient when it comes to crafting quantum algorithm. Making somehow, this is why I say crafting, making somehow use of this phenomenon. Okay? So now how does an actual circuit look like? You have this notion now. Now I want to present it from a developer's perspective. So everything new stuff. You never have seen it probably, yeah? So you typically have this stuff lines, and you have here those qubits, and you have also classical bits here. Yeah? So an algorithm typically looks like that. Then you have some initial state here in the qubits. Then you do some operations on them. As I mentioned, you just shift this vector in the block sphere somewhere. And you do also some like 2-qubit operations. I don't go into details, but this is an algorithm, and then somewhere at the end, you measure one or several of the qubits. And you project the actual state into a classical bit. So this is actually just what a quantum algorithm does on the quantum computer. Yeah? So having seen that, we can state, well, yeah, here, with great power comes great complexity. So how can we deal with all of that stuff? Yeah, because just imagine if we want to come up with quantum solutions, who thinks if some customer cares about that? Nobody cares, because we want to focus on actual solutions to bring benefits to companies. Yeah, so therefore we have the need of abstraction. And I want to put that in a broader picture. So how does let's say a quantum algorithm really look like? So we have seen first of the circuit. Yeah, okay, the circuit is actually executed on a quantum device. But how do we get this circuit on the quantum device? It's not just there out of thin air. Yeah. So what we have to do typically, we have a classical part of a algorithm. Yeah. And the classical part typically does all the pre-processing. You have to fetch data somewhere. You have to prepare it that you can then somehow create the actual quantum circuit. What we have seen is you have a classical program typically done developed in Python these days, yeah. And within Python, you describe those circuits, yeah. And of course, then you transpile them even in another intermediate language called QASM typically. And this is then sent over to a quantum computer via an API or an SDK, and then executed on the quantum computer. But you have always two parts. You have this quantum part, the actual circuit, which is executed on the quantum device. And of course, you have the classical part of your program, typically written in Python these days. Yeah? And of course, then you get also a result and have to do this some kind of post-processing. Yeah? So quantum algorithms are always hybrid in terms of some parts are run on classical hardware, especially preparing the circuits. Circuits are executed on the quantum device, results then are post-processed again on classical hardware. So, and now the situation gets even more weird, because it's a very heterogeneous field at the moment. We have lots of different SDKs and libraries out there which are available to develop actual quantum algorithms. And we have the situation that I talk here about crafting. It's not that kind of systematic software engineering which we are used to in the classical world. It's like algorithms stem typically from quantum physicists or theorists. Yeah, they typically don't care about implementations. They do theoretic stuff and provide you with algorithms, and you have to implement them. Yeah, to implement them, you have this bunch of technologies. Typically, the majority is currently driven by the data science community. Many work is done in Jupyter notebooks. So you all don't have this necessary software engineering stuff like continuous integration, continuous delivery, testing, etc. It's simply not there at the moment. Yeah? But therefore, also today we could state the question, well, okay, now if we once come up with a nice algorithm, which maybe has quantum advantage or something, how do I get it out of my Jupyter notebook, of my code snippets, towards actual customers? Yeah? Hiding these complexity. And to give you a more intuitive example, no? Go ahead. I brought a little case study with me. So I think it's quite easily to understand because I think we talked already about the traveling salesperson problem, but even if you think about, say, you have a whole fleet of parcel delivery vessels and you have some packages to deliver, and of course you have, for instance, here a dispatcher, then the question arises, well, how can I, which are the routes of each of the vessels has to take in order to minimize the let's say, fuel or so, yeah. And even this little example implies that we have to combine different parts, not just not everything is done in a quantum algorithm. We instead have to put and stitch different things together. First of all, again, here you see we have to transform input data from some. Next, we came up with a very easy solution. We first of all did a clustering of the whole graph. Yeah? The graph is the map of the city, for instance. Yeah, and to define, let's say, areas for each of the parcel delivery vessels, and then of course for each of those clusters we solved then the traveling salesperson problem. And of course, then we got back the result and had to transform it and feed it back to some scheduling software. Okay, so already here also see, well, it's not just about single quantum algorithms. It's always how they can work and bring us benefits, yeah, in a combination with other components. So therefore, we came up with several questions, which we then asked for the future. How, when it comes to how we can bring quantum algorithms to real life scenarios, and these are especially integration challenges we know from the past already. So we have to deal with the different technologies. As I stated, quantum algorithms are typically implemented today in Python. So tell me which enterprise application is written in Python who could easily integrate with those implementations. I know none. Yeah? We also have to think about the dependency management of all the systems, because if you use just Qiskit, for instance, of IBM, if you just use it, it feels like you download the whole internet of dependencies. Like this is really, you end up in a dependency hell as of today. Yeah? So we have to put much efforts in it that we just scaffold basic blocks of codes in order to implement actual algorithms. Yeah, etc., etc. So what we actually face are integration challenges when it comes to bringing those to life. And of course, you know, the Apification part steps in. What we then did, we tried to establish abstraction. So we figured out we have some, let's say, basic and general solution algorithms, and we could easily abstract them via an API. And of course, we have also, let's say, other parts of the whole program, which are more or less then an interface for the business use case. Yeah, and what does this brought us in the situation where we could easily change the implementations beyond, because they are not just the gate-based quantum computers, they are also, you have heard about the quantum annealers, and of course you can either send an optimization problem to a quantum annealer, or also with another implementation to a gate-based quantum computer, etc. So we were easily capable to change the implementations without changing the interfaces, actually. Yeah, and this brought us, of course, in the position where we now can say do some evolution in our code, in the quantum code, etc. And also, when new and bigger and more stable quantum computers evolve, we can change those implementations without affecting our, let's say, proof of concept implementations as a whole. Okay? And of course, we were able to not just integrate code snippets into, let's say, legacy systems, but we were also able to put overall APIs, product APIs, so to say, among whole sets of those components. Yeah. And of course, we figured out that there will be some very, very, very basic APIs in the future. For instance, APIs for communicating with a quantum computer and sending jobs on a quantum computer, but also APIs for like algorithms, as shown before, for solving optimization problems. Yeah, I mean, such kind of algorithm doesn't care about the actual use case. It's just a mathematical problem solution, so to say. Yeah, and what's then important to bring actual value into play is to provide use case specific APIs. For instance, in the traveling salesman solving is just optimization solving. Okay. But above this, we put another use case specific API for this parcel delivery stuff. So therefore, this very general service for solving the traveling salesperson problem got value by being very easily be used in those kind of scenarios. So how can an API become a product? Because it's not just about APIs, but it's also for the future, how can we create further value from them? Yeah, and we have to think about not just about those implementations like technical components which have to be stitched together, but we think also about them as being real products. So therefore, also the abstraction into APIs allows us to attach all those stuff like the technical specification, how to communicate it, service level agreements for customers. We can do a whole lifecycle managed by versioning the API, doing API evolution, etc. We can also bring monetization into play, like providing different subscription plans for a quantum solution. Yeah, of course we also add documentation to it, onboarding examples, and it's get really easy for, let's say, developers as we are to actually use quantum computers. Yeah, and of course, this is what I show you now on my last slides. This was also all was done in the course of a German lighthouse project called Planck. So everything what we have heard is our learnings from the Planck project, from our perspective as software developers, and this is also what I want to state as the nucleus of a quantum software community in Germany, because currently it's funded in Germany, but of course it's like an open ecosystem. And on the last slide, we also have some information how you can also participate in the future. Yeah? So first of all, some words about Planck. I think the first ideas from Planck about Planck date back to 2018, and you have to think about that we started thinking about quantum software back then. I think there were quantum computers with 5 qubits out there at that time. Yeah? But in Germany, the government understood quite quickly means here within 2 years, yeah, that we need that we need in order to make use of this technology. We have to start now to understand how we have to develop those things, those solutions, and how we have to bring them to real world use cases, and how we have to test real world use cases, yeah, against the technology. And here you see a brief overview of what the Planck as a project brought to life. Yeah, first of all, let's skip the marketplace. I will come back to that later. But we developed a whole serverless quantum platform, meaning that all this hassle with the integration stuff can be easily be wrapped into services, and this is supported by the Planck platform. Yeah. We have a collaboration platform, which might be very interesting for you, because different parties there from the platform, already from the Planck consortium, but also from over 80 associate partners are on this platform, and providing descriptions of algorithms, providing implementations of the algorithms, discussing algorithms, etc. We also plan to develop an orchestration platform based on those service capabilities, which I've shown you. in order to then be able to have this ecosystem of different developers stitching together different implementations also from other developers to make really use and reuse those services. And this is a perspective on frictionless, what we call frictionless quantum. So this is mainly the conceptual overview of what this serverless platform does and how it can help you to easily implement and reuse these kinds of quantum solutions. So first of all, maybe I think I should take this one. We currently develop development templates, so that you don't have to deal with all this dependency hell, as I mentioned, from technical point of view. That you can say, if I want to, for instance, I'm in the area of finance and I want to do some whatever portfolio optimization or so. Hey, there is something I can use, a template I can use. There are already scaffolded all the required dependencies, and they are of course tested, because you always end up in dependency hell with dependencies not working with each other. Then you can use those templates, develop your code, and of course then you can throw your code on the platform, on the service platform, which then puts an API around your implementation, which deploys it on the platform in a serverless manner, which means, of course, today we cannot earn money with those proof of concepts. So therefore, we created a platform which saves as much money as possible also for the developers. Meaning you don't have to pay anything when the service is not used, of course. Yeah, and of course the idea here is, you see that we have here the revenue sharing. If we make it that several developers develop different services with their specific knowledge, and they are reused in kinds of these orchestrations, like you do another implementation, but you don't rewrite a specific part of an application, but just reuse a service from another party. Of course, if your then API or services then used, or if you get some subscriptions from customer care, first, then there will be some kind of revenue sharing. So the idea behind this whole Blank platform, of course, is also kind of a platform economy to be established around all these quantum services in the future. And some final words about the Blank Research Project as a community, because this is really, we think this is a starting point for a quantum community. On this side, you see the consortial members. 3 years now, while we work together to build this platform, but also to test over 30 use cases. And testing means we try to figure out how these use cases have to be translated into, let's say, structures, inputs, etc., and which quantum algorithms might apply to solve those problems. Yeah? And all the learnings are then also reflected in the knowledge base in the community platform of the Blank project. And we already have over more than 80 associated partners, which are really eager to also get access to the system. And my last slide here, if you're interested in also, say, taking part in this community, then I invite you. We will start. I think we will start the open beta phase until the end of this year. And you are welcome to register for it, and you get an email when the actual sign up for new accounts or for external accounts is really open. So currently it's in a closed beta within the consortium, but until the end of the year you will be also able to take part in this community. And yeah, we also hope that we can open it up among whole Europe, of course. Thanks a lot.
Thank you very much. Sorry, I was lost. I was totally lost. I tried and I failed. But we can answer these questions, which are already here for like 3 hours now. And please stand next to the monitor so we can fit in the camera for the stream. Hey, guys. And so let's take a look at this, because I figured out and I heard that you want to use cloud somehow to prepare the algorithms and work with them. So do you know any major cloud providers that are bringing APIs for quantum computing?
So currently they don't think about in terms of APIs. They have SDKs there. For instance, IBM delivers Qiskit as a major SDK, and of course you will...
Somebody mentioned that. It's write it down. It's called Qiskit. It's Qiz. SKIT, yeah, and somebody mentioned that it's very well documented, that it's open,
it's good, yeah, it's
and that it's a good way and a good place to start. So just Google Quizkit, and somebody was hyping it a couple of hours ago here. So IBM and uses
for instance, IBM has Qiskit, and you will find in Qiskit some implementations already of algorithms. But this is more or less like you use them in your local machines and play around with them. It's not in this kind of service sense that I proposed here.
Okay, what's the shared revenue percentage? We're already doing business.
To be discussed.
Yeah, we're already there.
No, it's important. These are results of a research project. So we are now towards the phase where we try to productize, of course, the whole platform. So there are still many open questions with the monetization stuff.
Okay, any recommended reading? This is waiting here for a couple of hours too, about quantum computing, but for beginners, programmers who forgot most of the math.
It's really to get hard. It's really hard to get rid of the math, actually. So when you ever want to study some
he
kind
doesn't
of algorithm,
want to get rid of it. He just wants to remember it somehow faster.
So I think Qiskit is a good starting point. Yeah, because also on the internet page of Qiskit, you also have like how to start and doing
even with the
implementing
box sphere and everything. Do the vectors and everything.
Yeah, and also you also find something like implementing the first quantum algorithm, which is then a real random number generator, because quantum computers can generate real random numbers.
I would figure out that's one of the things that you can get some random numbers out of that.
This is kind of the Hello World example in quantum, generating random numbers.
Oh, finally, yeah. That's the first thing for which you can actually use it right now in 2022.
Indeed.
Okay, which languages are used to work with QC?
Yeah, typically it's all written in Python. Microsoft has also Q# in place, but this doesn't play a big role at the moment. It's all Python libraries, and Qiskit at the moment seems to be really. Maybe, yeah.
Don't you think we should go back to assembler?
How many?
Don't you think we should go back to assembler?
Actually, we do assembler because we transpiled this Qiskit Python code into QASM, which stands for quantum
I think if you're not depressed enough with math, then you should also try writing the code in assembler.
You could. QASM is human readable.
I remember that when I was 14. I just keep in mind the registers. What do I have in AX? What do I have in BX? And just go back to basics.
Indeed.
Okay, and then kill yourself. But okay. And who survives, he can start in Accenture. If we had access to futuristic quantum computer with perfect hardware, lots of qubits, which we don't actually need, could we immediately use Q algorithm to disrupt industries?
Indeed, yes.
Somebody mentioned that they did some calculations of where to put the sensors. There was a BMW car shown in the picture.
Yeah.
So for these,
Indeed, yeah, of course. And also, like if you could, let's say, solve the turning salesperson problem a bit more efficient, it would also be disruptive for some industries, etc. Or when it comes to simulating molecules or so. We had also, I think, in a previous talk, we had also this example. So, this would be have a huge impact.
I have an amateur question for you. Don't you feel bad that you're not doing any math or any discoveries, you're just trying to shoot and get some correct answers? And actually what I understand from this and from the neural networks, you're just trying to guess the answer. This is basically like mining Ethereum.
No,
don't you feel bad about that you're not going after the solution, like go A, B, C, D, and here's the solution. And you just go A, B, C, D, F, G to Z and everything, and let's try this for 5 days and let's do billions of operations. This is 97% of the solution.
But I think there are also basic strategies in formulating quantum algorithms. So, for instance, like shifting the probabilities in a way that it's most probable to measure the right solution. So, of course, it's just a probability, but you have some kinds of strategies. Because
this reminds me of like the restaurants at the end of the galaxy and probability drive and something like that. This is what I was reading as a kid in science fiction books, and somebody tries to do business out of this.
I think one of the main takeaways of this talk should be, well, if you as a computer scientist want to step into quantum computing, well, it's a completely different set of tools you have to master it, at least if you want to get an algorithm developed.
So shift from computing to guessing.
Yeah.
Okay. Perfect. So, okay, this is the future. Okay. This is what I don't understand. In your opinion, which encryption doom is more probable? General intelligence algos or quantum algos? Like,
I have no clue. I'm not an encryption specialist, actually.
Okay.
So at least.
But he's probably asking if we can break the crypto faster with the technology we have now or with quantum.
I mean, at least with Strauss algorithm, there's a theoretical proof that, for instance, RSA can be cracked in the future, of course, because we have much larger and more stable quantum computers for that. We have millions of qubits.
Okay, and one more question: how complicated tasks can be computed with Chinese quantum computer published some weeks ago?
I have no insight about this Chinese computer.
Really? I'm really surprised that they don't publish everything they do. I'm really Usually China is really open about stuff, and
it's even hard to get access to quantum computers from the US, because you get, but you have to pay. Wow.
Okay. This is international, I understand this.
Like, wow.
Okay, thank you very much. This was one of our last speakers. Thank you again.
Yeah, and it was a pleasure.
I managed to learn something.